Dendritic spines have a very small head, around 1 micrometer in diameter, that are separated from the dendrite by a slender neck. This peculiar morphology has inspired decades of theoretical and experimental work in an attempt to understand how excitatory synaptic inputs are processed, stored, and integrated in pyramidal neurons. However, due to this small size, probing the function of individual spines was not previously possible by the standard electrophysiological techniques. The development of two brilliant techniques that are used in this study, two-photon microscopy, which is shown on the left, and two-photon uncaging microscopy on the right, has allowed us to image and directly probe dendritic spines. The two-photon imaging provides depth penetration in live tissue in addition to two-photon absorption only in a focal plane. In addition, the longer wavelengths and lower excitation energy increases imaging depth in scattering tissue such as brain, while also reducing photo damage and toxicity compared to one-photon imaging. On the other hand, synaptic inputs in individual spines can be mimicked via two-photon uncaging of cage neurotransmitters. In this technique, the cage neurotransmitter can be released from its cage only in a focal plane to mimic presynaptic release at a single spine. This small excitation volume thus confers the ability to photoactivate molecules with high spatial precision, thereby providing novel opportunity for the study of spine physiology. The configuration of simultaneous uncaging of cage neurotransmitter and calcium imaging of events in single spines allows us to probe the electrical and biochemical processes at the level of a single spine during synaptic transmission and plasticity. A widespread approach for combining two-photon uncaging of cage neurotransmitters with two-photon imaging in the activated spines is to use two-pulse lasers. One laser for two-photon uncaging of cage neurotransmitters such as MNI glutamate, for which we need to use 720 nanometer excitation light, and a second laser for two-photon excitation of calcium indicators such as fluorophore, for which we need 800 nanometer excitation light. The approach is, however, costly. In a paper published in 2019, Dr. Araya described a method that consists of a cost-effective one-laser source two-photon microscope, capable of nearly simultaneous two-photon uncaging of neurotransmitters and two-photon calcium imaging of the activated spines using a single wavelength, with low laser power for calcium imaging, meaning a power not sufficient to result in any partial uncaging of the cage glutamate, and short, high laser power pulses to uncage caged glutamate. Here on the right, you see the schematic representation of a scanning period during a single trial, wherein each thin black line represents the beginning of a new frame scan, and each black box represents a single average image being generated. A switch box allows for the switch between the imaging and photoactivating mode, which happens in less than 2 milliseconds. In E again, note the very brief interruption in the imaging during the uncaging. F is showing you that the activation of a single spine by two-photon uncaging of glutamate reliably induces somatic EPSPs. You are seeing average of 20 depolarizations. And G is a two-photon image of the spine from a layer 5 pyramidal neuron, and the red dot represents the uncaging spot. As mentioned, a main feature of two-photon glutamate uncaging is that it allows for the precise activation of a single spine. To test the two-photon uncaging spatial resolution, in the same paper, they used single-spine uncaging spatial resolution to rapidly and precisely mimic synaptic activation of single spines while synchronously recording the EPSP at the soma. They targeted the laser at 6 different locations that were located at a range of distance from the head of the spine. The first 3 locations are shown in Figure C. Importantly, uncaging at locations further from the spine head generated smaller EPSPs. To validate that the imaging laser power does not inadvertently uncage glutamate, they looked at the frequency and the amplitude of EPSPs during periods where the laser was off, or it was at the imaging power, while they were scanning a dendritic spine. In E, you see that the amplitude and the frequency of the EPSPs, they were similar during the periods where the laser was off versus at the imaging laser power. Recent studies have revealed that the morphology of the spine, head, and neck are modified dynamically during various forms of synaptic plasticity. The most extensively studied forms of synaptic plasticity are long-term potentiation (LTP) and long-term depression (LTD). In the early 1970s, Bliss and his colleagues reported that the repetitive activation of Schaffer collateral axons using high-frequency electrical stimulation can result in a potentiation of synaptic strings that could last for hours or even days. The mechanism underlying this form of synaptic potentiation is summarized on the right. Briefly, a large NMDA receptor-dependent increase in calcium in the dendritic spine can activate a signaling cascades such as protein kinases, most importantly CAM kinase 2, which promotes the incorporation of additional AMPA receptors into the spine. In parallel, it's been shown that dendritic spine head enlargement is happened after the LTP. In contrast, in the LTD, a modest increase in postsynaptic calcium concentration due to the modest activation of NMDA receptors lead to the preferential activation of protein phosphatases. That leads to the dissociation of AMPA receptors from their molecular scaffolds and their lateral movement to the periphery of postsynaptic densities, where they are endocytosed and potentially degraded. There is evidence that LTT is accompanied by a shrinkage of the size of the dendritic spine, and this may be due to the loss of AMPA receptors. Many studies have demonstrated that LTP and LTD are associated with spine enlargement and shrinkage, respectively. In fact, a change in spine volume has been considered to be an important substrate of synaptic plasticity. In this regard, using the two-photon glutamate uncaging technique, while simultaneously imaging the morphology of the stimulated spine, in this figure they are showing that the repetitive glutamate uncaging under low magnesium conditions induces a rapid and transient enlargement of the spine head in the first few minutes in the hippocampal CA1 pyramidal neurons, and this is followed by a volume change sustained for hours. Spine enlargements with similar time course have also been observed in response to standard LTP induction protocol. Interestingly, due to the biochemical confinement of the spine head that will be explained in the next slide, these morphological and functional changes are observed only in the stimulated spine, but not in the neighboring spines, indicating that LTP can be induced in an input-specific manner at a single spine level. The compartmentalization of dendritic spines can be broadly divided into two functional domains: the biochemical compartment and the electrical compartment. The biochemical compartment describes the spatial confinement of biochemical signaling due to diffusional restriction and physical segregation of proteins and signaling molecules. Indeed, the spines are diffusionally restricted from dendrites and compartmentalize calcium after synaptic stimulation. This local biochemistry and the high calcium accumulations observed following temporal pairing of neuronal input and output are thought to be responsible for input-specific synaptic plasticity. The electrical compartment, on the other hand, describes how spine neck morphology can impact the kinetics and propagation of synaptic potentials in a spine-specific manner, which we talk about it in the next slide. As mentioned, spines serve as electrical compartments because of the resistance at the neck. Indeed, the electrical compartmentalization amplifies local EPSPs within the spine, and like that, produces a voltage gradient between the spine and the dendritic shaft, thus reducing dendritic and somatic EPSPs compared with those in the spine. Interestingly, a previous study by Dr. Araya using whole cell recordings with glutamate engaging at individual spines revealed that the stimulation of spines with longer necks produces smaller EPSPs at the soma in the layer 5 pyramidal neurons. In other words, he has shown that in cortical pyramidal neurons, the amplitude of the engaging evoked spine potentials recorded at the soma are inversely proportional to the length of the spine neck, with long-necked spines having small or negligible somatic voltage contributions.